Hello students, and welcome for our physics lessons. We are going to do Form 3 topic, proceeding from where I stopped last time. The topic is linear motions, the first topic in Form 3. And to confirm that we're in class, please send us an SMS to 21450. I take the number again, please, to confirm that we're in class and you have a book and a pen ready to learn physics with us. It is 21450, the number to SMS to. All right. In our previous lesson, we started introducing this topic, whereby we started by discussing the terms associated with linear motions. That is, we discussed speed is the distance of a time taken by body. Then we went to velocity, whereby we said velocity is a vector quantity, which is the speed in a specified directions. Then we went further to define the displacement, which you say displacement, just like vector velocity, is a vector quantity which is defined as a distance in a specified directions. That's the velocity. Then the last term that we discussed is acceleration, which we said accelerations is the rate of change of velocity with time. The rate of change of velocity with time, and I think that's where we stopped. And we can now take up one example involving accelerations. So let's take one example. Example 1 that says the velocity of a body increases from 72 kilometers per hour to 144 kilometers per hour in 10 seconds. The velocity of a body increases from 72 kilometers per hour to 144 kilometers per hour, and this change in velocity took 10 seconds. Calculate its accelerations. So what is the accelerations? So as I said from the definition of accelerations, that acceleration is actually change of velocity with time. So writing that in formula, we can write accelerations is equals to change in velocity. That means you must consider the final velocity, which we said in our previous discussions, that final velocity let me first of all use the word equations. Final velocity minus initial velocity. We define that change by the time taken. But in physics, instead of now writing the word equation like that, once we said we normally use acceleration, we normally use symbol A. Then we have the final velocity, which we said we use V. These are conventional symbols. Anybody who does physics understand what we are talking about here. Final velocity is actually V minus initial is U divided by T. T is time taken. Those are the conventional symbols for these ones. So it's good in physics now to write what you have. We have the initial acceleration, the initial velocity, which is U, is actually 72 kilometers per hour, and this changed to 144 kilometers per hour. And what time did it take for this velocity to change? It only took 10 seconds. So those are the units. This, we have the initial velocity, we have the final velocity, and then we have the time. So what we require to do is now to calculate the acceleration. So as I said, that we normally work with SI units, so we cannot now work with kilometers per hour. So we must, the first thing that we do is to change the velocities into meters per seconds, whereby I said this is 72 kilometers per hour, so which we said we must change into meters per seconds, and I said we do that by multiplying by 5/18. So 72 kilometers per hour, we multiply by 5/18. This one we are doing to change it into meters per seconds. So this gives us by 18 by 18, 18 gonna be all by 9 2 by 9 8 by 2 1 by 2 4. This giving us 20 meters per second. 20 meters per seconds. So this was now gives us 20 meters per second. We have converted that ones into meters per second. Sorry. Then we have this other one, 174, 144. We still do the same. And now that this is actually double this, we can automatically see it's going to be 40 meters per second, because 144 is actually a double of 72. So, but we can still do that once to have 144 kilometers per hour. We multiply that by the fraction that we said must multiply all these values to convert them into meters per second. So we multiply by 5/18, just like what we have done in the first ones. So we can say here by 2, we can divide by 2, we get 9 by 2, 72, by 9, 1 by 9, 8. So as you see, we get 40 meters per second. So now we have the initial velocity, we have the final velocity in the right units, and we have the time. We don't have to convert time because the SI unit for time is seconds. So now what we need to do is substitute those values in our equations. So we have accelerations is v final velocity, which is 40 meters per second. Then you have the initial velocity, which is 20 meters per second, and the time it took for that velocity change is 10 seconds. So we divide by 10. 40 minus 20 is 20 meters per second. Divide by 10, we see we get this 2 meters per second squared. So we said the unit for measuring accelerations is meters per second squared, because velocity itself is meters per second, then we are dividing by second again, so it becomes meters per second squared. So we see this is a body that is increasing in velocity. 2 meters per second is increasing. But as I said, that in case we get a negative value, what does that show? It shows that this body is decelerating, what we called retardations or decelerations. So that's how we work out a problem involving accelerations. That first, we must confirm that we're working with the right units, that's meters per second. Then we write what we have first, confirm the units. Then from there, we write our equations. That acceleration is v minus u divided by time, where v is the final velocity, u is the initial velocity divided by time taken for that velocity change. Then from there, now we blow it up, we write the answer there and align it. Next, we are going now to go to the graphs of linear motions. We need to know how to sketch some graphs associated with linear motions. So what we call the motion graph. So motion graph. There are various graphs that we can draw that involves now linear motions, and we are going to start with the first ones. The first one, that is the distance time graph. So for me, I'm just going to sketch to show you how we can actually sketch some graphs of these linear motions. And the first one, as I've said, is the distance time graph. And the distance, the first one takes the y-axis. So we have the distance time graph. So we have the distance is on the y-axis, and then we must label our axis. So the distance is in meters. Then we have now on the x-axis, we have time, and then we must write the units in brackets. So the distance time graph is in that shape. The distance on the y-axis, we have time on the x-axis. Then from there now, we can have now various graphs depending with the state of the body. So the first ones, suppose we are drawing the graph of a body that's not moving, that's stationary. How would it look like? So a body that is stationary, like my duster here, the time is moving, the time is progressing, but the distance is not moving. So for that ones, we would show it with a straight line. So this is a graph of a stationary body. And from this you can see that the line increases on the x-axis, but on the y-axis there's no increase or decrease. That shows that the body is stationary. Time moves, but the distance on the y-axis, we see there's no change. So that is the graph of a stationary body. The other one is, that's Roman 1. Still a distance time graph. We draw two axes like that on a Cartesian plane. Here we have the distance in meters, and here we have time in seconds. That one must always be shown. And then suppose it is like that. How does it show? Let's try to analyze it. That if I demarcate this curve like that, suppose this is 10, this is 2, this is 4, this is 20, we can see that there is there's equal change in time with the distance. That as the distance moves from 0 to 20, the time has changed from now 0 to 2 seconds. And the same interval is also here, from 10 meters to 20 meters, and from 2 to 4. As the distance increases, there's equal change of distance with time. So we say that such a graph is a body moving with constant speed. Constant speed. Because why do I say speed? Because here we have the distance. So from this graph itself, the gradient would give us the speed. So suppose I draw a triangle there. On what I have on the y-axis, what I have on the y-axis is the distance, and what I have, the change in x-axis, give me time. Meaning that when I get the gradient of such a curve, it's going to be uniform. So this is a body moving with, I think I would have used the word uniform, is a body moving with uniform speed throughout. The rate of change of the distance with time is the same. It's uniform. That's another one there. The other one is the third one. We can have a distance here, and here we have time in seconds. But in this case, the rate of change of distance with times is varying. It's not constant. So how would you show that once? It can be like that. That's the first scenario. Or it can be like this. See, this is distance and this is time in seconds. So in both of these cases, we see that the rate of change of distance with time is varying. So the speed is varying. But here we see that it is increasing. It's varying, yes, but increasing. It's non-uniform. Then this one's here is varying, yes, but almost decreasing. Because we see from here, it's almost becoming flat. The gradient is becoming less or less steep. So it's both of them, yes, we are saying is varying speed. But looking at it further, we can see that this is a body that's moving at a varying speed but increasing. The rate of change of distance with time is not the same as we actually show in the second in our second diagram there. Here the rate of change of distance with time is the same. If I can have another one here, it can have 30, and you can still guess now the time it will be. It's going to be 6, because the rate of change of distance with time is the same. But for these ones, the rate of change of distance with time is not the same. That's why I'm saying it's as a body moving with varying speed but increasing, as opposed to these ones. Varying, yes, but decreasing. So those are some of distance time graphs. Therefore we can go to the other ones. That is the speed time graph. The speed time graph. Just like for the distance time graph, when we're also sketching the speed time graph, the speed, it must be on the y-axis, and the speed, we must label our axis very clearly. When we're drawing any graph, it's good to label our axis. So we have on the y-axis, we have the speed here in meters per seconds, and then we have time here in seconds. That is the graphing of the speed time graph. Then we can have now say various scenarios. Speed, we have time. Suppose this was I do like this. What's that it show? We have the speed here in meters per second. Here we have time. Suppose this is 20 meters per second. How can we translate from this graph that this is a body moving with the same speed? It's a body moving with the same speed throughout. 20 meters per second throughout. Time is moving, but there's no change. There's no change in speed. So it's a body moving with the same speed. The other one that we can actually draw out of this, we can have speed, we can have time here, and as usual we must show the units. But in this case now, we draw a straight line like that. What can we translate from this speed time graph? Looking at it from here, we can see at this point here, it is 0, 0, showing that at time 0, when the body was at rest, the speed was 0. Maybe at 2 seconds, the speed was, let's say, maybe 10 meters per second. At 4 seconds, the speed is, let's say, maybe 40 meters per second. So we can say this is a body that there's increase in speed, and this increase in speed, it is uniform. So this is a body that's moving. This increase of speed is increasing with time and uniformly. This uniform increase in speed. This uniform increase in speed. So again, that is now the speed time graphs. Speed on the y-axis, time on the x-axis, but then we can show various types of graph depending with how the body is. Very quickly now we can look how we can sketch the other one, that is the distance, the third one now, the distance time graph. Sorry, not the distance, but the displacement. The displacement. We said in physics, the word displacement does not mean distance, because I said in our ordinary day life, we normally use them to mean the same. But to say displacement is a vector quantity. Both of them are measured in meters, but distance, we said from the definitions, is the total length of the path taken by a body. But for the displacement, we said it's a speed in a specified direction, meaning we must give the magnitude and the direction. So that's a difference, just reminding you. So again, for the displacement, we have the displacement here in meters per second, and then here we have time in seconds. But the first graph here, for a stationary body, for the displacement, we must show or above the axis and below. Because why is that? Because this displacement being a vector quantity, it can be both positive or negative depending with the position of the observer. So we must show it above or below, because displacement a vector quantity, it can be positive or negative because of the positions of the observer. For now, we are going to stop there, and right after the break, we are going to look at other motion graphs. And for any comments, questions or opinion, please SMS to 21126. I take it again that for any opinion, questions or comments, please don't hesitate to write to us and text message to the number 21126. Thank you for listening to me.